Okay, I would say it's nice to be here, but I'm always here. This is a very exciting meeting. I stumbled into this subject by accident. In my seminar, Pratik, who spoke this morning, was giving a beautiful talk, which I was sleeping through. And at one point, he showed a formula. And Adam woke me up and said, there's a PDE in here. And that's what started all this. So here we go. Okay. So the first thing we're going to talk about is deep relaxation, PDEs for optimizing deep neural nets, joint with all these guys. We have t-shirts that we could distribute with the following picture. Here it is. Local entropy, which was mentioned by Pratik, is a way of smoothing F so that you can do gradient descent on a non-convex function and do a better job. It's as simple as that. He arrived at it through stochastic physics and whatnot, but there is a PD connecting this sort of thing. We have this crazy non-convex function over there, which of course will live in very high dimensions, but here we're just showing a one-dimensional problem. And what we're going to do is sort of convexify it. That is, piecewise convexify it this way. Keep the minima, if we can, and make it more or less piecewise convex. And then there's another thing which we do, which is a more smoothing version of that. So there are three graphs over here, and I want to show you how to get both of these two from this one in high dimensions. Now, of course, the reason we're doing this is that it's easier to do gradient descent on functions like this. So here we go. So this all started with so-called entropy SGD with all these authors, but Pratik was the first author. The idea was to minimize a highly non-convex high-dimensional function in n dimensions, of course, n large. And what you did was replace f by f sub t, and this is the moment of truth, where f sub t is the log of the Green's function for the heat equation convolved with the exponential of f of x. And there are good reasons why he arrived at it, but I'll skip all those and talk about what we discovered, the connection between this and PDE. And I made a career, or at least or a tenth of a career, out of introducing PDE into image processing. So God willing, the same thing will happen here. Okay. All right, here we go. So what are we going to do? Revelation. That function f sub t, u of xt, satisfies a viscous Hamilton-Jacobi-Burgers PDE, of all things. Okay, so there hasn't been too much PDE done here in the last couple of days, but I love it. It turns out that if you solve the initial value problem for this PDE, and that's in very high dimensions, how do you do it? We'll talk about that. You get exactly the formula that miraculously appeared before. You get this formula. And why is that good? First of all, why is it true? It's true because there's a Cole-Haff transformation. I'll skip a lot of the details. But if you take the log, minus the log of v, and set that equal to u, which means v is equal to exponential minus u, you satisfy the heat equation by God. And this was an exercise in a book in 1905 or something, rediscovered by Cole and Haff, and it's has a nice long life. So the solution to that PDE is exactly what we did by smoothing f, which is kind of nice. I'll skip the details because I have about 75 slides, but trust me, it's okay. Well, the nice thing about this is this widens local minima, narrows local maxima, in fact removes them in some crazy way, and raises minima a bit because of that stupid viscosity term. So if you go back and look at it, the equation we're satisfying is ut plus 1/2 grad u squared is equal to 1/2 Laplacian u. We're going to get rid of the Laplacian and improve things. There's a better procedure, I maintain. That is, you take the solution to the problem without the viscosity. And if you go back one more time, what that will do, if you can solve it, which you can do in 2 dimensions, is give you that, from that crazy initial function f, you will get this piecewise convex function, more or less, with wider minima and maxima disappearing as we speak. Okay? So that's a nice thing. And I'll demonstrate why that's true. So the question is, how in God's name can you solve a PDE in 100,000 or a million dimensions? And the answer is carefully. There's a formula due to Peter Lax and Olenek and God knows who else, probably Hoff, which says the exact answer is nothing but the prox of f of y. So it hasn't been too much. I mean, Tom blew me away when he said prehistoric convex optimization. It's like 3 years ago or something. This is really hot stuff when we were doing total variation, all these other things, and doing fast methods. Now it's so passé. But anyway, here it is. This is the proximal of f of y. So the solution to that PD of all things is precisely 1 over t times the Moreau envelope, whatever that means. You see what it means right there, of t times f of y. And the idea is to do gradient descent on this function rather than the original one, and things improve. Okay? They improve so much that what you get looks completely trivial, and that's embarrassing, but it's useful. Okay? So the min of this thing is called the prox, and the proximal method, which is classical and not used very much because there's other methods for convex functions, is to let xk plus 1 iterate that way. It's arg min of f of y plus 1 over a previous time step, y minus xk squared. We take small delta tk first, large or later. So what you got is the following. If you minimize this thing, you have f of xk plus 1. I'll skip the details. You can see that the f of x is decreasing. And if you go back to the original function, the smaller dt is, the more convex this thing. So why is this better than the original function? Well, it's better because for small values of dt, this is convex. So you sort of climb up there if you can. Mm-hmm. So that's the solution to that PD, and that's a slight improvement. That's an improvement over or related to what Pratik had done earlier. If you carry this out, by God, what do you get? You get backward Euler, which is pretty mindless. But basically, that's all this is. Instead of doing gradient descent, you make it implicit. And in principle, that improves things tremendously. And you can actually prove that if you could do this, it would be a wonderful thing because you would widen minima and get rid of maxima, and you'd be in great shape. Of course, this is not so easy because eventually it's non-convex and you have to get the right minimum. But you can do inner loops and stuff like that, and we do. And the effect is very good. And I'll skip some of the details, but you can show that f diminishes, it converges perhaps to a local minimum, or if it converges to a global minimum if you do it right. But here's my favorite part of this, and this is real PDE, so hold on to your hat. In one dimension, I want to show you why you widen minima and why you remove maxima. And it has to do with driving. It has to do with rarefaction waves and shocks. If you look at the one-dimensional version of this thing, the equation is Berger's equation, ut plus ux squared equals 0. I'm sorry, I mean, it's Hamilton. This is called Hamilton-Jacobi. This is called conservation laws, and this was really hot stuff at one point. So I'm trying to revive it. So the solution to the conservation law, if you differentiate, it gives you the slope. It gives you the gradient of this function. And you can write it implicitly this way. So hang in there. It's not that complicated. It's an implicit function. And I will try to motivate it a little bit. So so there's a few lines of calculation. But the bottom line is that if f is convex in some interval and concave outside the interval, and the px is, there's a inflection point, it's going to move to the right. You're going to widen, if you take a sine wave, you will widen the bottom part, narrow the upper part, and it will disappear eventually. And you get that nice picture. This is kind of cool. And this is what's behind this ESGD, which is an improvement of SGD, which is what Pratik was talking about. So that's the first part of my talk. Questions or anything before I zip along? So this is turned into an algorithm called ESGD if you do inner loops, and it works better than SGD, according to everybody who uses it. And it's not that complicated. Now, okay, so I haven't finished yet, sorry. So my little analysis showed that the convex part has moved to the right, past its right endpoint, and moved to the left past its left endpoint. It widens minimal regions, narrows and shrinks maxima, and maxima disappear in principle. So it's a nice smoothing and it's easy to implement. And now for something completely different. Okay. Here we go. So again, my goal is to bring in differential equations into this crazy subject. So we're going to talk about deep learning with data-dependent implicit activation functions. This is a joint work with Bao Wang, who's sitting in the first row, will answer all questions. And Zhushang Shi, who's really a smart guy, who did some nice interpolation. So this is stuff that you all know well. I will skip it. These two important types of deep neural nets, VGG, ResNets, wide applications. Here's Tom's picture, which I stole. And I will not take any questions about that. Okay. He's my student, so poor guy. Okay, so deeper is better is the moral of the story if the network is appropriately designed. So here we go, ResNet. I love this formulation. It looks like a dynamical system. xi plus 1 is equal to xi plus f. If you take xi plus 1 minus xi, divide by dt, you have a differential equation. So why wouldn't anybody do it this way? My God. Okay, all right. And so what we're going to do is look at this as a control problem, a simple one to state. U sub t plus v dot grad u equals 0. We want to find v, and that's the training. V is the training, period. U of x1 is given. That's at t equals 1. You have initial data, which is the training set, so it's sparse. And the idea is to treat this as a control problem. So ResNet can be considered as a forward Euler solver to the control problem. Solve this OD, sorry, not PD, what am I saying? But the simple linear PD is not linear because V is going to depend insanely on everything that came before it. But nevertheless, it's easy to write down in this abstract formula. And it's a forward Euler solver. And here is the key part of what we're going to do. We're going to extend the labels on a label subset to the set of points that we care about. And you'll have to believe me, we have the best way of doing this. That is, this is called weighted non-local Laplacian. And it's been very, very useful in, for example, filling in missing data in images, basically. If you subsample an image and you do the graph Laplacian on it and try and solve that with given data, it doesn't work that well. But if you put these weights, which I'm going to tell you about in a second, in front of the points that you know, it works terrifically well. It's a very simple idea. Professor Zhusheng Shi was the first person to realize that to look at the graph Laplacian to solve it requires a little bit of numerical analysis. And it makes it much, much better. So I'll talk about that. So this is a way of interpolating very sparse data. And if I was a good salesman, I would take a picture of Barbara now and show you what we can do, but it really does do a very good job on images. Okay. So suppose you only have a tiny amount of data which is labeled. You have an Euler-Lagrange equation, which is a simple one. I mean, it's basically a Laplace equation with weights. And you have this term P over S minus 1, which is big at points where you know the data. And the ratio of unknown points to known points minus 1 is what you do. This is called the weighted non-local Laplacian. It's a mindlessly simple idea. You just, you have a bunch of sparse points on a grid, let's say, and you put big weights on those points where you know the data, and then you minimize the Laplacian with the extra weights at those points. And there is some probabilistic analysis that indicates you need about n log n points to be labeled. And how do you find the weight functions? Approximate nearest neighbor searching. There's a whole bunch of stuff on that. So there's some numerical stuff. And what are we going to do with this? Well, we have a vanilla deep neural network. And we're going to use weighted non-local Laplacian as the final thing, not the usual thing. And there's an issue about back propagation because this is a complicated implicit function. So we finesse this by some dangerous method, which seems to work. Here's the architecture. It's a buffer block. And in words, you train the network with only linear activation functions to steady state. Then you run a few training epochs on the network where you freeze the DNN and linear activation blocks and only fine-tune the buffer block. In other words, we sort of linearize this thing. I mean, it's a cheat, but we try to get the best linear function we can. And after all, Laplacian u equals 0, linear functions solve it. That's an overstatement. So that's the idea. This is a control theory problem that we are solving in this crazy way and trying to get the velocity field. And I'll give you numerical results, which are pretty good. Okay, so here, look at CFAR, for example. So here's the accuracy of some simple classifiers, different data sets. So this is very encouraging. I mean, WNLL does well in these small problems, which encourages us to go further. With the guys on the right. Here's the plots of generation accuracy over training procedure. On the right, we have WNLL, and on the left, we have brand X, which is the vanilla method. And you can see there are improvements. We get past that local minimum. We drop down and pop up again. And we eventually get higher, and we go up faster. And I'll give you numerical results soon. So again, the basic idea is it's a control problem, and you use the initial data, which you interpolate, to be what you finally want to wind up at. And how do you get there? And you get there with solving this control problem. Okay, so this is a taming of the degradation, not the generation. A problem of vanilla DNN by weighted non-local Laplacian. You can see on the right, and on the left also for that matter. On the left we have 1,000 training data, right, 10,000. And we have 3 different networks, and we can see that when the vanilla networks become deeper, the generation error does not decay. Does decay, actually. It does not decay. What am I saying? That 2 double negatives. I ain't saying, okay. While the weighted non-local Laplacian fixes this. So we do much better in this situation. Okay. And here are some super duper numbers. The generalization error rate of the whole test set of vanilla DNNs and WNLLs trained over the entire and first 10,000, 5,000, 1,000. Meeting of 5 independent trials. To make a long story short, we do very well indeed. For example, look at this 43% versus 29% for vanilla with 1,000 and so on. So we get significant improvements by doing this. We're talking on the order of 5. You'll see the numbers are consistent. Here's a performance on CFAR 100. We have, what do we have? 5% improvement, for example, which I guess is a big deal in this subject. Am I finished already with this thing? Okay. Okay, so the summary is that you have a data-dependent implicit activation. You backpropagate the gradient of a harmonic function by some kludge, linear function. And there might be a better way. In fact, we think there are better ways. And we seem to resolve the degradation problem. We get a 20 to 30% accuracy improvement on CFAR 10 and CFAR 100. And we can reduce the model size. And the paper's online. So I got more. I have 5 topics, so this is 2. We'll be here till midnight. So any questions on this stuff? Yep.
This Laplacian, is it explicitly computed?
Oh, yeah.
Is it symmetric?
Yeah. All of the above. You were minimizing grad u squared where you, so it has to be symmetric, where grad is a weighted, has weights in front of certain points. Very simple. These papers exist, and I should tell you the king of this stuff is Zhushang Shi. He realized that when you solve the graph Laplacian, you got to be careful. You have to do special things at the points that you know to make sure that they actually take on the data, and then you get an incredible interpolation. You really do. Okay. So that's part 2. Here comes part 3. It's going to look familiar because it's related to what Tom just talked about. This is binary relaxation. Again, I'm trying to bring in PDE. So this time we're not bringing in PDE, but we're bringing in prehistoric optimization techniques, like primal dual hybrid gradient, for example. This was done in joint work with Peng Hang, who's sitting here, and Jack Shin, also sitting here, and 3 other people. Okay. So quantized, I don't have to give you the pitch, Tom did, but I'll say it again. You have huge number of floating point weights pose challenges to the deployment of DNNs. I'm reading this. Floating point weights are not essential to achieve good accuracy. You can benefit from quantized low bit weights. You have less storage, faster inference, and so on. And the new processes for AI applications are featuring 8-bit vector operations, so there's motivation for doing this. So here's a mathematical formulation, and we're going to do something which is different from what Tom was talking about. You want to minimize summation I equal 1 to n subject to x belongs to q, where q is a set of quantized weights. So you're going to project, basically, when you do gradient descent. You have to live back in q. And you have quantization discussed below. Okay, so this is typical optimization. So the quantization of a floating weight vector gives rise to a projection problem. You arg min of x belonging to some set x minus y squared. It's equivalent to k-means clustering. But we're not going to use that. It's Lloyd's algorithm is unpractical here. There are empirical schemes, but here's what we're going to do. We're going to do something which is very related to what Tom did. He did half of it. I mean, your prediction thing, I guess, was primal dual hybrid gradient. This is the prox, which plays a big role. So if you do this kind of stuff, you learn to love this operator. And I'm sure most of you have seen it before, many of you. You take g of x, and you, one more time, g of z, whatever, and you solve the Hamilton-Jacobi equation with initial values g of z up to time t. But any sane person would say that's the formula. Okay. So what we're going to do is replace g, which was the following. Okay. We're going to replace the this is a very simple idea, and it works very well. You take the characteristic function of a set, which is 0 if you're in the set, infinity otherwise, and take the Moreau envelope of that, which is an approximation to the characteristic function. And it's basically equal to 1 over a constant, small constant, times the distance squared to the boundary, which makes sense. It's infinite when t goes to 0, and it's 0 inside the region. So what we've done is taken a very simple idea. We take the indicator function and smooth it, and then the world is yours. Good things happen when that happens. And it's as follows. So instead of minimizing f of x, you minimize f of x plus 1 over t times the distance from x to q squared. And you do hybrid gradient descent plus the proximal mapping, which means that you take this gradient descent on this modified function, and then take a second step, which is iterative, like that. And this seems to skip bad local minima. So binary relax is a 2-phase algorithm like this. And the second step is exact quantization. It resembles linearized Bregman algorithm, which is very nostalgic. It's, so the idea of relaxing the discrete sparsity constraint into a continuous, it's not non-convex, why did I say non-convex? Into a continuous regularizer, which is certainly non-convex, certainly convex, L1 norm. That's been very successful. You heard Mickey talking about stuff like that for compressed sensing. So here are our experimental results. And again, the idea was very simple. We just smoothed via the prox the indicator function and used that. We did layer-wise quantization. And ours, again, I just showed tables, seems to win in these examples, okay, against other binarization schemes, here too, for that matter. Okay. And the pictures look nice, same thing. But this so-called binary relaxed, this is the pièce de résistance. We get the full precision 32-bit accuracy using 4-bit weights on ImageNet classification with this thing. And it's fast. And it's very easy to program. It's a couple of lines, basically. So I think I've finished part 3. Any questions about this? So you're shocked out there. Okay. Am I doing time-wise? Let me see. And here are some references, and all this stuff is online. Okay, and here is something which has nothing to do with compressed sensing, but I love, sorry, compressed sensing, nostalgia. With deep learning. It's phase retrieval, which is a classical problem, but I'm bringing it in because it's using some of the same techniques. We have non-convexities. We're going to use prox galore and duality and all that good stuff. All the tricks that you borrow from convex analysis, even though things aren't very convex and things seem to work. So phase retrieval is an interesting problem. This is maybe the wrong audience, but anyway, it's fun. Given the magnitudes of the Fourier coefficients of something, find the image. What? It was crazy. But you have some extra information. We're going to take a geometry that looks like, this is done with Min Pham, who's back there. Any questions? No, it's okay. So this is what it looks like. You have a region in space, and in the middle, there is something of interest. And outside of it, everything is 0 on the grid. So that's extra information. And you have the Fourier coefficients of the whole caboodle, which include the data in the middle, which is the interesting part, and the fact that, and you have a lot of constraints. The solution, the function is 0 elsewhere. So again, we're going to have a projection. And again, we're going to smooth. So if there's anything to take away from this lecture besides the fact that PDE can do anything, the proximal is a good thing to use when you're dealing with indicator functions. It's a great thing to use. It smooths it, and it makes life easier. I mean, it's more convex. So the inverse problem I'm going to solve, if I can try to zip through this, is minimizing f of u. F of u is an indicator function. That means that the bottom line is that u is equal to 0 in some region, and greater, and that's the only place. U is 0 outside of D, and the indicator function is infinity, which means you have to live inside D. So you're minimizing that indicator, that function u, such that z is equal to f of u. This is a classical this is the classic problem. This is a very non-convex problem, to put it mildly. I mean, everything is non-convex. The constraint z equals m is certainly non-convex. And there's also noise galore. So we're doing real physical data done with Professor Miao and physics group, who made a big name for himself doing this stuff a long time ago. So this is phase retrieval. This is what it looks like. And there are classical methods that are used called, which are basically alternating projections, more or less the same kind of thing that Tom said you shouldn't use, alternating projection methods. And there are people who are more hip and use hybrid input-output, which has Douglas-Ratchford type stuff. So we have to denoise and we have to recover the Fourier coefficients just knowing their magnitudes, which is fairly amazing. Okay, so there's a couple of tricks that we use. Basically, the first thing we do is take, one more time, take the, this is kind of a new idea, which is fun and very useful. We take the prox of v, f of v, sorry, that indicator function, which is a wild coincidence that it happened in 2 different places for the same function. And something very interesting can be done. There's something called, which I'm sure we didn't invent. We take a, instead of taking a general a v minus u squared, you can take v minus u inner product g v minus u, where g is a positive definite matrix. That gives you a lot of flexibility, and it helps with the smoothing. And I think it's a really cool idea. It's a generalization solving a different Hamilton-Jacobi equation. I always think in those terms. So it's a different kind of update. You can you can take its prox, and it turns out to be written in an easy way down below. In dual space, its dual is equal to the dual of the original function plus y transpose gy. Okay, I'll try not to overwhelm you with technical details. But the basic idea is that you can solve the final problem by this Shambo-Pock primal dual hybrid gradient method. And you have noise in Fourier space. And so I love the fact that if you want to smooth a function in Fourier space, what you do is take the function in physical space and multiply it by the magnitude of x squared, more or less. That's the Laplacian when you go backwards. Okay, so that's kind of cool, and that was done. So this is a rather simple algorithm. It's primal dual hybrid gradient with all these proxies in there. And we have computed this with various possibilities. Either we use the Laplacian as a regularizer, or the identity, or some combination of that and magnitude of x squared. There are parameters galore, but the basic idea is quite simple. I'll give you the code. And the dual variable is, has a nice interpretation. Y is the subgradient of f. And y is the orthogonal complement of projection of u onto that space. Okay. So there's the algorithm that was used before. This is what we do. It's not much more complicated. But it's kind of fun because we're bouncing back and forth between Fourier space and physical space. And we are trying, one more time, we're trying to recover phases of functions, the Fourier coefficients, knowing that only their magnitudes and knowing where a lot of zeros are, basically. And there's some physical results, which I can now show you. And basically, all I'm going to do is show you that our stuff is better than what came before. But you can save computational costs by around a factor of 20. Okay, more of the same. The histogram shows that we zero in, and the right answer is. And we converge faster. I mean, we get a deeper minimum considerably. I'm going to skip this graph because it drives me crazy. Okay, this is what these things look like. And our stuff has a smaller error on the right, and people in the know can see that, I guess. But my favorite thing is the histogram, where we zero in on the right answer pretty well. Okay. Nanorice. And again, the histogram is my favorite. And these are results that were done. So we gave the code to somebody else, in our physics colleague's lab, and he validated what we did. He did it on real data, and we do considerably better, as you can see, for the mean of 100 reconstructions. And the dear old histogram with various parameters involved. And I think I'm almost finished. Well, this is the best one. Here comes more of the same. Thank you. And any questions?